Okay, so it is time to continue.
Why so sad?
Wow, there is a lot of optimism in young eyes. So Professor Nekrasov is going to continue his course, and the rest you know better than me.
Actually, this is not what I meant to say. Sorry. Okay, so today we turn the page and introduce a new cast of characters, which will hopefully turn out to be the cast of all characters, and so eventually we'll reunite the second half of the course with the first half of the course. So to speed things up, I will make a jump. So what I'm going to talk about is supersymmetric gauge theory in 4, 5, 6 dimensions, but I will spare you the details and translate it to a class of statistical mechanical models, but I will skip the word mechanical. So we will be studying essentially probability measures or complexified probability measures. This is actually, I noticed that in this corner something happens. Okay, so measures on the set of multi partitions. So this way we'll make contact with several lectures at the school. For example, a lecture by Professor Schlossman, who just arrived. And also lecture by Sasha Veselov. And also, of course, lectures by Professor Kunkov. So these measures will depend on many parameters. And so it will take some time to introduce all the details. So I apologize. If you've never seen them, I'm sorry for you. But if you've seen them and you kind of get used to them, you learn to love them. So these are very interesting natural measures. Also related to the lecture by Grisha Alshansky yesterday, of course. Okay, so let me first. So what are the multi-partitions? So let's first let me remind you what are the partitions. So partitions are denoted by letter lambda, and they are there are many ways to think about them. So one is to say that this is a collection of non-negative integers. And so it is a partition. So in this way, this is a partition of an integer number, which is denoted usually as absolute value of lambda. It's called the size, and which is just the sum. And then the number of integers in in the sequence is called the length. Oops. Now they can geometrically we can visualize them by drawing a diagram. It's called the Young diagram. So this is what you saw many times already. So it's a picture where now we introduce a collection of boxes. So the total number is equal to the size, and the number of rows, the number of boxes in the first row is lambda 1. The number of boxes in the second row is lambda 2, and so on. And we can coordinatize, so introduce labels to keep track of individual boxes. So my notations are flipped compared to Sasha's notation. So index I goes vertically, so I labels rows, and J labels columns. And so this is the box with coordinates ij. And so sometimes we'll write that the box belongs to lambda, meaning, and box is really just a pair of non-negative integers. And so saying that the box ij belongs to lambda is the same thing as to say that the integer j is between 1 and lambda I. And you can also flip, so do the reflection along the diagonal and get a Young diagram of a different partition, which is called lambda transposed. And this is defined by this relation. So the boxes of lambda and lambda transposed have coordinates which are just exchanged. So there is a finite number of partitions of given size, but of course, if we don't restrict the size, it's an infinite set. And it's a set which can be organized in a graph. So this is, okay, so this is called Young diagram. And just by looking at this picture, you can see that you can define some kind of a growth process where given the partition, given the Young diagram, you can attach a box to this diagram and produce another diagram, or you can remove a box. And so there is a procedure. So you start with nothing, and with to nothing you can attach just one box. And so that's so the first two vertices of this graph, and then to one box you can attach a box to the right, or you can attach it from below. And then from here you can either continue this way, or you can go up here. And if you like, we can orient it. And so it continues. Continues indefinitely. So this is Young graph. So it's an infinite graph whose vertices are partitions, and two partitions are connected by an edge if there is a way to obtain one from another by adding or removing a box. And if you want to know your options given the partition, so this is partition lambda. So if I'm already sitting somewhere in Young graph, and I want to know where can I go from here, so by looking at the diagram, I see that there is a certain number of corners where I can attach a box. And so the collection of these boxes I will call the positive boundary of lambda. and there is a certain number of boxes which can be removed. And so this will be called the negative boundary of lambda. And we can compute the number. I mean, the number, the cardinalities of these two sets can be pretty random, but there is an index, there is a topological invariant, which says that the number of positive boundary minus negative boundary boxes differ exactly by 1. So if you just start from here, these two match, these two match, these two match, and then this one is not matched. Now there is a further way of kind of capturing the information about the shape of the diagram, and that's a character of the diagram, which I will also denote sometimes as chi lambda of two indeterminates Q1 and Q2, and this is just the sum over the boxes in the diagram, Q1 to the power I minus 1, Q2 to the power j minus 1. So if you are given this function, you can reconstruct the partition and vice versa. It's a definition, yes. Well, it is also a theorem, but yes, very, very good. It's to formulate the theorem, I need to give you yet another definition of what partitions are, and so this definition becomes kind of meaningful if we identify lambdas partitions with the set of monomial ideals in the ring of polynomials in two variables of finite codimension, so of codimension absolute value of lambda. So from the lectures of Andre, you know everything there is to know about this ring, and so today he was explaining to you what does it mean to sit at the origin. By what's the Cazul resolution of the skyscraper shift at the origin, and it was actually perfectly illustrated by the attempt of the chairman to stop the talk. So if you want to fix the moment in space and time in algebraic geometry, you cannot just say that I'm going to sit here. You have to say that I'm sitting here, but if I make a step, I will be multiplied by the function which vanishes at this in this direction, and if I make that step. And so this is dense of the resolution, and that's what we're going to do now to understand these boundaries. So what's the monomial ideal? Monomial ideal is the ideal which is generated by monomials. So it means that for some integers I, a and b, and the requirement that it is of finite codimension. So it has several generators. So there are several generators. So I goes from 1 to, I don't know, there is some number of generators. And so to understand what it takes to make the ideal of finite codimension, we need to. Okay, now I need to borrow the picture from Andre's talk, and so draw it again, except that I will change the notation from x to z. And we will achieve x to z by doing this, of course. So this is the monomial 1, and this is the monomial z1, and this is the monomial z2, z1 squared, and this is z2, and so on. And so I apologize I lack the patience to draw a more realistic ideal. But whatever, so if you have an ideal which is, if you have a monomial which is in this ideal, so somewhere here, z1 to the power a, z2 to the power b, then everything which is to the right and above of it will be in the ideal by definition. So ideal is what is invariant under the multiplication by polynomials. So if this is an ideal, then any monomial multiplying it will be also an ideal. So if you have some set of generators, they will cut out certain portion of this positive quadrant. And now if I want the complement to the shaded region to be finite, then it means that it has to come up here somewhere. It has to come up here somewhere. And so if you draw this boundary, you will see something which looks like a Young diagram, except that it is flipped upside down. So that means that among those AI, BIs, there must be one where B is 0, and there must be one when A is 0. So that, but now more importantly, if you look at this picture, you see now what is the meaning of the blue boxes. So the blue boxes are these guys. So this is, okay, so the monomial ideal is actually generated by, okay, if I'm, so it is generated by monomials of this form when I goes from 1 to the length of the partition. And so the boxes in the outer boundary are precisely the generators of I lambda. So Young diagram itself represents the quotient. So the Young diagram so the expressions, the monomials of the form z1 to the power I minus 1, z2 to the power j minus 1, when I and j belong to the partition, they, if you like, they can be chosen as a basis of the quotient space, and that's the space which let me call it K sub lambda, and this finite dimensional by the requirement of the codimension being the size of lambda. So so the maximal value given I, j can achieve is lambda I, and so if I make this so the exponent make it one higher, then I'm already inside the ideal, and that's in fact a generator. And so these are the generators. Now, actually, the actual number of blue boxes is smaller than, could be smaller than the list here, because this is a it's exhaustive list, but it's not minimal. So the blue boxes are a minimal set of generators. What I mean by what I just said was that in this list, there is a box in this, there is this box, which is not needed as far as the ideal is concerned, because this is already in the, is generated by this blue guy. Now, what about the red guys? Well, usually, so these are generators. Okay, I see. These are So there are generators, but there are also relations. So if you look at this box here, it can be obtained by multiplying this blue box by some power of z1, and it can also be obtained by multiplying this monomial by some power of z2. So there's a relation in this ideal which connects things which are generated by different generators. And so these corner boxes, which I denote there in the red, are in one-to-one correspondence with these relations. And so bottom line is that delta plus corresponds to generators of the monomial ideal associated with lambda, and delta minus are associated with the relations. So now, to make this well, not exactly that. Sorry. Yes. So that's what I said. I said one-to-one correspondence. So there's one-to-one correspondence with this box and that box. I just I like to historically, it happened historically, is that if you like Young diagrams and you think about how they change, so these are the boxes you care about, because this is what you remove, this is what you add. But in the formulas which we will be dealing with, we actually deal with those boxes which are always outside. But these ones are related by just shift by Q1, Q2. So now another way of saying what is to be a monomial, does it mean to be a monomial ideal? It means that it is invariant under the C star cross C star action, which rotates Z1 and Z2. So, and therefore, this quotient space becomes a representation of this two-dimensional torus. And this character is the character of C star cross C star action on K lambda. So this is a theorem now. The theorem which is proven by just direct observation of this picture. So the monomial which sits here is the eigenfunction of this torus with the eigenvalue t1 to the power of I minus 1, t2 to the power of j minus 1. And I chose letters q1 and q2 instead of t1 and t2 to confuse Vanya. So that's my, all right, but what about these generators and relations, and what's is there a way of somehow enumerating, keeping track of these blue and red boxes? It turns out, yes, there is a way to sorry, could you say it louder? So this vector space, K sub lambda, it's a vector space, which is a representation of this two-dimensional torus. Not every space is a representation of it. No, I mean, okay, so if, yes, as a abelian group, a representation splits into sum of one-dimensional representations. But not every ideal in the ring of polynomials will lead to a representation of the torus. Because if you take the ideal generated by, let's say, Z1 to 5 plus Z2, and Z2 cubed, for example, it will not be invariant on the direction of the torus. So in fact, so the torus will move it to another ideal. And so if you think about the space of all ideals, the torus acts on the space of all ideals, but some of them are invariant. And so these are precisely I lambdas. This is not monomial, and which is the same thing. It's synonymous to not being torus invariant. Okay, so now I need to introduce another quantity which is related to chi, which is 1 minus which I claim it is precisely the sum of so this virtual character keeps track of the sorry, I should have used the colors. So this is from the colorblind days. Where I use the notation for the content. So this is the refined version of the content used by Sasha Veselov. So the content of the box, ij, is a linear function of I and j with slopes log q1, log q2. And so I claim that knowing the character of the partition by doing this algebraic manipulation, you'll extract two characters, so one with the plus sign, one with the minus sign, and those will give you precisely those blue and red boxes. And that's essentially just repeating what I said about the generators and relations. So you already know this, actually. You have seen this an hour ago. So this is essentially the calculation of Kazul resolution, but with at the level of characters. So so there is one. So suppose lambda was empty, for example, nothing. So then S lambda is equal to 1. And that's just the fact that for empty partition, there is one box which you can add. And that's one, which is here. So it's easy to understand what is the ratio of S lambda divided by 1 minus Q1, 1 minus Q2. Well, this is just the sum of all ij such that z1 to the I minus 1, z2 to the j minus 1 belongs to the ideal of q1 minus 1, q2 to the j minus 1. Why is that? Well, what did I do? I just computed. So I took this quantity, which is just the sum of over all positive monomials. And then I subtracted chi lambda, which is the sum over all monomials which are inside my Young diagram. So the remaining monomials here are precisely the ones which were in the ideal. Now let me try to represent this ideal in terms of generators and relations. So every generator spans a cone. I think it's a cone in your sense, right? You had cones, right? Yes. So there is a cone. So for every blue box, I draw. So let me draw it like that. So this is the sum over blue boxes. So every blue box, spawns children. So these children are the monomials which are divisible by this box. And so this is the sum is the character of all monomials which are spawned by the generators. But in the actual ideal, I've counted certain monomials more than once. So there are children which are shared, kind of joint custody. So so everything which is here is already accounted for by the descendants of this monomial and descendants of this monomial. So I'm subtracting them. Say it again? Yeah, so, well, no, there are of course custody battles because some can be claimed by many parents, but if I do kind of start from here and subtract one by one, then it comes to a peaceful resolution eventually. So, and so there is a factor of Q1, Q2 precisely because of what Senya observed, that I'm looking at the internal corners, and they are related by a shift to the ones outside. Okay, so this is clear. So now there is a little bit of homological algebra. So this is some identity on characters, but there is also what's now called categorification. So there is a complex, actually maybe a tautological complex, associated to the partition lambda, and that's a complex I should put here space Q and here space lambda of Q, where Q is C2, and I always make this mistake. It is probably the dual space to the space on which my polynomials are functions. Maybe not. So what is this? So this is map sigma and tau, or like differential d1 and d2, and so d1 takes a representative of the of this quotient space, and multiplies it by the coordinates. So z1 k, z2 k, and projects down to the quotient and puts 0 in here. And g2 takes the triple k1, k2, and the number u, and sends it to I guess u plus z2 k1 minus z1 k2. Right. So so it is easy to check that the composition is equal to 0. And I mean, if you were careful, if you watched Andre carefully, this part is part of the Koszul complex. Because it's essentially it's a multiplication by a vector, and then external multiplication. Follow the definitions. Let's not worry about it. So, well, see, so this is, what do you mean? It appears here. So it's part of this map. Well, now the question is, what is the cohomology? So this complex has interesting cohomology, and this cohomology is trivial in degree 2, and it's non-trivial in degrees 1 and 0. And so the claim is that this is precisely the character of the first cohomology of this complex, and this is the character of the zero cohomology of this complex. No, character. So a character is a representation of the torus. This complex is the important thing is that this is C star cross C star equivariant. So every term in this complex is a representation of the torus. Here I take the trivial representation, and the map is equivariant. So see, Q is taken to be it's a defining representation of this torus. So yes, what's the question? And because it's equivariant, the cohomology will also be representations of the torus. And so that's the sorry, not this. This is not what I meant. This is what I meant. This is actually the cohomology, the character of the, okay, maybe character of H1. And this is the character of H0. Well, think about it. What is, let's do it on this picture. So what is the cohomology in degree 0? So this is just the kernel of D1. It's just the kernel of D1. So what is the kernel of D1? Well, these are the elements of the space of my quotient space. That is to say, some linear combinations of the boxes, which vanish when you multiply them both either by which vanish when you multiply them by Z1 and vanish when you multiply them by Z2. Vanish in the quotient space. And so how does Z1 and Z2 act? Well, multiplication by Z1 simply shifts you one position down, and multiplication by Z2 shifts you one position to the right. So this box here, for example, vanishes when you multiply it by Z2, but doesn't vanish when you multiply it by Z1. But these red ones, they have nowhere to go. Sorry, what do you mean? You mean to move the picture, or you want? Okay. So I just shown that the kernel of the differential D1 is precisely spanned by the vectors corresponding to the red boxes. And so that's and so this is the character of H0. I'm not sure about my shift by Q1, Q2, but okay. And it is a little bit less obvious, but I invite you to check that this character, you see, when I computed this quantity for you, I called it a virtual character. It's not a character of a vector space, because some exponents come with plus sign, some exponents come with minus sign. But it's a virtual representation of the torus, and it is a difference of two actual representations of the torus. And now I've presented to you what are these representations. This is H1 and this is H0. And the fact that there is no cohomology in degree 2 is a cute exercise in Lagrange interpolation formula. Also known as discrete differences. Yes. I apologize. Okay, so now that we've somewhat familiarized ourselves with partitions, I can hit you with multi-partitions. You know, we are told that we should live on multiple planes of reality, and so the good object to study is not one. I mean, you can have a lot of fun just working on a set of just partitions, but for we will need multi-set. So now I have to multi-partition. It's just a collection of partitions. And alpha will belong to some finite set, which we will specify later. Okay, now the measures. So what are the measures? So ultimately, what we want to do, we want to compute some kind of partition function, which will be the sum over the multi-set of partitions. And so there will be a measure which depends on the shape of these partitions and will depend on some parameters. Typically, there will be some set A. So now there are three theories. So cohomological, K-theoretic, and elliptic. And the only difference is that so in cohomological theory you use rational functions, in K-theory you use trigonometric functions, in elliptic theory you use elliptic functions, and there are limits reducing elliptic theory to anything below. So I can write formulas maybe in elliptic category to begin with. So in physics language, this would correspond to the 4-dimensional, 5-dimensional compactified on a circle, and 6-dimensional theory compactified on an elliptic curve. You're not, okay. So to motivate, well, there are, I mean, the origin of these measures is the from localization in elliptic homology of some moduli spaces. And these are modular spaces of solutions to some partial differential equations. The equations are defined on R4. And so this R4 plus the 2 dimensions of the elliptic curve, they make this 6. And if you do K theory, there is a hidden circle there, and that gives you 5. Right. Well, you see, the cohomology theories are associated with groups, and so you need a group law. And if you classify possible group laws, the elliptic curve is where the buck stops. Which doesn't mean that we cannot have 6-dimensional theory compactified on the high genus Riemann surface. It's just that the genus of the Riemann surface will be encoded in the set A. So, okay, so I promised you a bag of tricks. I have many tricks. It's just that I'm giving you. I'm just I'm taking some. Only one pile of them. But indeed, there are mu's associated with higher genus surfaces, but they expressed in terms of the rational function. So they only admit a cohomological treatment. So there is no even K-theoretic version of it, as far as I know. Okay, so I did not explain it. No, I did not explain it. Yeah. No, it's just that this curve is not the curve which encodes the type of the measure. It's the curve encodes the type of the set A. I did not explain. I mean, I didn't write a single formula yet for. So mu. So what? I mean, there is a lot of details in the set of indices here, and what kind of measure is there, and so. Okay, the question. So the formulas tend to be pretty long. So maybe it's easier to start with a simple example and then go up in complexity. So let me start with an example where my set A will be just the set of integers from 1 to n, and they will be treated on equal footing, so I call them colors. And so my measure in this case will, so the parameters, so this example is called A0 hat example. So the parameters are the collection of complex numbers. So this n is this, and 3 additional complex numbers, which I will actually make into 4, but require that they sum to 0. And the last parameter q, which I will denote by q slash, so as not to confuse it with q1 and q2, and it's going to be the elliptic curve parameter, although it is not obvious from the outside that there is any relation to elliptic curve here. So this is, I'll denote it by e to 2 pi tau, and so tau. So these are my parameters. And so the measure, in this case, okay, so there will be, first of all, just a sum of all sizes. So once again, the random variables are just a collection of n partitions. Now, I need to look into my notes. All right, so we'll have the product over ij in lambda beta. So my product is over pairs of indices alpha and beta, but here I'm taking the product over boxes in only one of the two diagrams, which I can associate to this thing. But in the contribution of this box knows about the other diagram. And I can put here the theta function. And theta function will, so when I write theta of x, depending on whether I'm in cohomological K-theoretic or elliptic theory, this could be x, it could be 1 to the minus e to the minus x, or it could be the product 1 to infinity, 1 minus p slash n minus 1 e to the minus x, 1 minus p to the n e to the x. So the elliptic theory depends on its own, on another parameter p, which is the so this is another elliptic curve which has nothing to do with this elliptic curve. Okay. And so I don't even count it in my parameters because it's just part of the ground field. All right, and okay, now so I should have written this in a smarter way. So this is the product ij epsilon 3 plus the same thing. Times, unfortunately, I have to go to this board, product over ij of the diagram alpha, and there is something like the conjugation going on here. So it's lambda j alpha. Sorry, this is lambda transpose. So one thing which you can always remember, so lambdas have index I and lambda transpose have index j. So that's my bookkeeping. Right. So so transposed 1 minus I plus epsilon 2 j minus lambda beta I. And here's plus the same thing. Okay, so it looks pretty terrible, but it is actually not that bad. there is a way to understand this. So let's first so in this product there are terms when alpha is equal to beta. So in this case, so if alpha is equal to beta, then the quantities which appear here have a name. So if I'm sitting at the box ij, then so lambda I is the number of boxes in this row. So the quantity lambda I minus j is the number of boxes to the right of that box. It is called the arm. It's called the arm. And similarly, there is the number of boxes in this column is lambda j transposed. And so this quantity lambda j transposed minus I is called the leg of the box ij. So what we have here are the generalized arms and legs. So this is arm plus 1, and this is minus leg. Except that for general, so if I have a pair of diagrams, I can actually define the arm and leg of the box of one diagram relative to another diagram. And so sometimes this quantity can be negative. Now, there is a special case of these measures. So this is what happens when alpha is not equal to beta, right? So for example, this is alpha, this is lambda alpha, and this is lambda beta. So then typically you will have both positive and negative expressions. You may also get 0, but when alpha is equal to beta, you never get 0. Oh, I'm sorry. Most important thing, my parameter is a. So everywhere I should add an a alpha minus a beta. A alpha. Otherwise you might get 0 in denominator. And here the claim is that for theorem, if you like. Is there interaction between what? Yes, you see, it's a I have lambda beta, lambda alpha. A alpha minus a beta. So no, of course they interact. So one way which Young diagrams have not been presented here, I think, yet. Did you have this picture? Not yet. So. No? Okay. So one way to think about this ensemble is that you have diagrams. So Young diagram, if I rotate it by 135 degrees, it will look like now I call it a pile of bricks thrown into the cart, or the gardening cart, which grow over points a1, an, and these points are actually complex. So think of this as a complex line. Say it again. Well, it's my drawing is bad. Yeah. So, I mean, these are rectangular bricks. Sorry. And in some sense, the sizes of the sides are epsilon 1 and epsilon 2. Okay. And it should be epsilon 1, epsilon 2, but sometimes it looks like it's epsilon 1 minus epsilon 2. It's actually complex, yes. So actually what happens is that on the complex plane, you have a growth process which start with seeds at the points A1, AN, and the growth is with steps epsilon 1 and epsilon 2. So these are points, so this is A1 plus epsilon 1, A1 plus 2 epsilon 1, A1 plus epsilon 2, A1 plus epsilon 1 plus epsilon 2. And the diagram, Young diagram, is just the boundary of this process. Maybe I should have, sorry. The boundary is somewhat outside. And so this, and these boundaries somehow interact. So there is some kind of a potential. So there is some sort of potential between, which sort of attracts or repels the corner boxes which we discussed earlier. So the blue ones and the red ones. So this is some kind of dipoles. Some kind of dipole. Interaction. So it's a discrete process. So my charges are allowed to occupy only certain positions. But if you decipher this point, you get something like Coulomb gas actually, but Coulomb gas of dipoles. Now, there is of course a simplest case. So this formula makes sense, makes perfect sense for n equals to 1. So if n equals to 1, we can simplify. So there are no a's in this case. So then we'll have just the sum over a single Young diagram, q to the power lambda, and then the product over boxes in a single box. So then we'll just have theta of epsilon 1 minus leg of the box plus epsilon 2 arm plus 1, epsilon 1 leg plus 1 minus epsilon 2 arm. Now, yes, epsilon 3 is called adjoint mass for the initiated. And so is epsilon 4, which is negative epsilon 1 plus epsilon 3. So there is a symmetry. It's not obvious, but there is a symmetry which exchanges. So there are interesting symmetries of this expression. You can exchange epsilon 1, epsilon 2. You can exchange epsilon 3 with epsilon 4. The epsilon 4 is defined through this relation. Now, remarkably, this can be summed up. I will not bother you with the formula for the elliptic case, even for K-theoretic case. Let me. So in the rational case, when theta is just this argument, this is summed up to the remarkably simple formula. So this is the denominator which you saw in Senya's talk. So this is one of the so if epsilon 3 were equal to 0, this is the conspiracy of this formula. If epsilon 3 is equal to 0, then there is a complete cancellation. And so it becomes just a uniform measure. And then you're just counting partitions with the weight by the size. So this is what you would have gotten, and that's the famous Euler computation reproduced by Professor Schlossmann a couple of days ago. But if epsilon 1, epsilon 2, epsilon 3 are non-zero, then it turns out it's not very much different. It's probably minus 1. So it's just the complex power. What do you mean? Only an exponent, yes. Only an exponent. And so there is a, by the way, what's my time constraint? Okay. So, okay, so there is an interesting story about this formula. So there is a special case. This is the full formula. This is n equals 1, so it's not the interesting, not the most interesting case. But okay, maybe I should not spend too much time on it. But just so there is a special case which is related to the representation theory of a symmetric group. So this is in this case, this measure, let's say epsilon 3 goes to infinity, and q goes to 0, so that epsilon 3 squared q is fixed. So okay. limits, interesting limits. So then this measure simplifies, and it becomes the Plancherel measure studied by Vershik and Kerov. So this is the famous hook formula. So this is the product over the boxes of 1 over the hook length squared. So what is the hook? The hook is the arm plus the leg plus 1. And so if you don't take the limit epsilon 3, so they studied, yeah, I mean they were interested in what's called the microcanonical ensemble, where they fix the size of Young diagram and send it to infinity, right? So we work. So in physics, there are two sometimes equivalent approaches. You can work in the canonical ensemble, in the ground canonical ensemble, where you don't fix the size, but you fix the fugacity. And then sending the size to infinity corresponds to taking the limit when the fugacity goes to infinity. And so it's equivalent. So you can get the limit shape from that. Yes, so one of the stories of this whole, I don't know, tale or ballad is the study of the asymptotics of these measures when the parameters epsilon 1 and epsilon 2 or epsilon 2 go to 0. So and that's the story of limit shapes. So limit shape in this language would be when you send epsilon 1 to 0, keeping lambda fixed. So more generally, sorry. Yes.
I was afraid you're going to erase this photo.
No.
Something I wanted to say.
Yes, please.
So this is related to rigidity of Kirchner generally. What the theta function formula says? It says that the Kirchner genus of the Hilbert scheme of points equals the orbifold Kirchner genus
Of the symmetric product. Right. Yeah. So this is something like the elliptic genus of C2. Not elliptic genus, but like this, like homological expression. So if you do it in elliptic homology, what is trivial is doesn't look trivial on the blackboard. It's something like a platistic exponent, which is what symmetric product does. Yeah, it's okay. For the experts, let me explain. So this is we're not alone. So we think that we live in R4, which is C2, but it's not just C2. It's a C2 which sits inside C4. And so you see, I have 4 parameters: epsilon 1, epsilon 2, epsilon 3, epsilon 4. So there is a 4-dimensional space hiding in this story. And our C2 is just a sliver of the reality, just a 2-dimensional plane inside a 4-dimensional space on which acts a 3-dimensional torus. 3-dimensional because I have a constraint. And so this is the, so it's a 3-dimensional torus. It's a torus of SL4. So it's something which preserves the volume form. And so it's C2, which is kind of abstracted. It's C2 with a bundle, precisely bundle over it, 2-dimensional bundle, and the epsilon 3, epsilon 4 are the weights of this bundle. Okay, so to make contact with Stas' lecture. Okay, I did not explain much. So this is what Andrei said was that this is actually an integral sum over n, 0 to infinity, q to the n, and then there is an integral in the sense of elliptic homology integral, elliptic over the Hilbert scheme of n points on C2 of the equivariant Euler class, or Chern. So what would it be? It would be like okay, in the language that Andrei was using, it's the integral of the wedge of exterior algebra of the cotangent bundle. And so this is, of course, so it's minus 1 to the I. And yeah. So if you didn't put here anything, and if you remember his lecture, that means that you are taking the cotangent bundle, and then you look at the zero section and look for the zeros of a generic section. So it's like Euler characteristics. But we want to make our life more interesting, so we weight these factors not with -1, but with e to the I don't know, -1 to the e to the q3 to the power I. So q3 is e to the epsilon 3. And now you can ask, how come I've broken the symmetry between 3 and 4? But because of the symplectic nature of, because it's a symplectic manifold, well, you can check from this formula that actually you can exchange it from 3 and epsilon 4.
So if we did 3 and 4 are because of cotangent bundle. If you remove T star, you will get pretty much a measure of the cells, corresponding to Young diagram. Right? I'm just trying to clarify the connection of epsilon 3 and epsilon 4. Is it because of T star, cotangent bundle?
Yes, it's because of T star. Yeah, it's because of T star. Well, okay. This is okay. T star is actually an effective description for something more profound, but it's For the purposes of this calculation, it's because of T star. So the way I wrote it here, this is this works already in elliptic homology. So this is, think of this as a class in elliptic homology. So
Your original status formula was without T star. Simply count the measure of the cells, corresponding cells, which are given to arms and legs, right?
no, this is, you see, this is the denominator. So denominator comes from the tangent space to the Hilbert scheme itself. And then the numerator comes from whatever class you want to integrate over it. So no, it was an original formula. It was an original. Okay, so to make okay, so for general n, life is not so simple. In fact, already for n equals to 2, and right, for n equals to 2, this partition function already describes conformal blocks of 2D CFT on an elliptic curve with a parameter q with one puncture. So if Stas were to do what he was doing yesterday on the two-dimensional torus as opposed to a domain, and he had a specific defect inserted there, and he took a continuous limit, and then he managed to factorize it into the product of holomorphic and anti-holomorphic objects. The holomorphic object would turn out to be, I'm sorry, I erased half of that, but okay. How to what? Yeah, you have pairs of Young diagrams. Pairs of Young diagrams. N equals 2 means pairs. Liouville. Okay, since I have only like 1 minute left, yes. Right. So as yesterday was explained, everything is related to everything. So pairs of Young diagrams are related to representation theory of GL2 hat. And inside the GL2 hat, there is SL2 hat. And there is Drinfeld-Sokolov, which gives you Virasor out of SL2 hat, which is the symmetry of the Liouville theory. So this is, I mean, it's roughly the explanation. Okay. So there is a part which, so one Young diagram is almost trivial because it corresponds to just a free boson. And so that's why this is to Liouville. Liouville plus free boson, actually. So we need to decouple these factors. Okay, so tomorrow we'll introduce a new tool for studying these partition functions and studying expectation values there, and this new tool is called the QQ character. So there will be no what? No, this is too simple. No, forget about that. So what do you want? No, it's a new special function. It's a conformal block of Liouville theory. It's a special function. I mean, when Q goes to 0, it reduces to hypergeometric functions, and then you can expand it to hypergeometric functions. But okay, sometimes, since I have parameters, I can play with parameters. Sometimes, if there are some rational relations between epsilons or a's, things can simplify. So sometimes you get hypergeometric functions just without taking limits. I want to finish by saying that okay, you may worry that I have things in denominator, and things in denominator sometimes vanish, and sometimes you get poles. So the poles are when A alpha minus A beta plus epsilon 1 times. So poles at when I and j are both greater than 1. But sometimes these poles are not so bad. So they are, sorry, what do
You mean that some of them actually cancel?
sometimes they cancel, right? So, for example, if epsilon 1 over, so if the ratio of epsilon 1 to epsilon 2 is a positive rational number, then the individual contributions will have poles. There will be poles, but they cancel. So, and that has to do with the fact that the fixed point set in the modular space, for example, in the Hilbert scheme of points, is not isolated. No, that's not. This is not the way I put it. No, that's not the way I put it. But compact. And if you have a pole when A's are involved, then it's this fixed point set is non-compact, and you have an actual singularity, actual pole. Okay, so let's stop for now.
So you just.
I'm finished. I have. Okay.
Oh, there is five
sorry,
minutes, but so at least
sorry,
you can
I misunderstood your.
You can no. Less than 10 minutes, but it's still.
Okay.
You should at least make some maybe conclusion, some maybe fix what you said, because.
Okay. So
some people I believe are lost.
All right. So what are we trying to achieve here? So we are. So we are. So I've defined. I didn't explain where I got it from, but I defined some measure, which I can normalize on the set of multi-partitions, and we want to study expectation values of some observables. So by definition. So all evaluated on lambda. So, and the claim is that there are observables so observables are just functions on this set of multi-partitions, some functions of set of multi-partitions, for which expectation values solve interesting equations. And so equations are Knižnik-Zamolodchikov equation,
For which current algebra?
Pilavin, Polyakov. Zamolodchikov. It all depends on the choice of observable. So it's a clever. It's a game. So I give you observable, then you prove that it solves this equation. So BPZ for Virasoro, and now people pushed it to W3, maybe WN. Spin chains. So they could be wave functions of spin chains. Of AD spin chains, and also AD hat. And the partition function itself, so Z, as a function of epsilon 1, epsilon 2, if you take the limit when both epsilon 1 and epsilon 2 go to 0, has the, with the proper normalization, has the asymptotics, which, so this leading singularity depends on epsilon 3, q, whatever parameters are left, and this is the prepotential of some special Kähler geometry. Special Kähler is one word. I mean, it's not a geometry, also known as Rabi-Bruton geometry. And so quite often there is a family of curves with Krichyver data which capture these asymptotics. So it's and asymptotics at the level of these Young diagrams corresponds to the limit shape problem. So it's a generalization, kind of vast generalization of Vershik-Kerov problem. And also there are other interesting limits when epsilon 2 goes to 0 and epsilon 1 is fixed. So this partition function still keeps surprising. So there's an interesting asymptotics with less singularity. So it has now additional parameter. And so that describes, well, in a sense, it describes the deformation of special geometry, and you can call it quantization. And sometimes it is quantization, and sometimes it's a classical geometry, but in a rotated complex structure. So let's discuss it in more detail. This is a famous Cherednik mistake. It's a twisted superpotential.
Okay. Okay. So that.
Yes.
That was
celebrated.
That was an announcement for
Yes.
2 other lectures. Yeah.
Yes,
One of which is kind of
exercise
a half a year course.
Yeah.
Okay.
No, we will not go through all of that. Our goal is
I believe, yes.
Our goal is to connect to specifically elliptic Calogero-Moser system.
I see.
Or maybe number of particles. For n, for capital N, the measure which I described with this ace, with n ace, describes the quantization and deformation of elliptic Calogero-Moser system with n particles. N is n.
No, there is.
Yes.
There is elliptic Calogero-Moser because there is an elliptic curve. On the blackboard there is nothing.
Is
just
governed
nothing.
by the
Just
parameter
nothing.
q. It's by the elliptic curve parameter. Because these measures, they
Which
are
is different from the previous
small
lecture.
deformations of uniform measure. So the series is kind of dominated by the uniform measure, which is just the nth power of the Dedekind function. Yes, Kolya. Oh my God! Yes. It turns out that elliptic Calogero-Moser is actually related to the A0 hat spin chain.
And it's for theta not being elliptic, yeah? Not
Yeah, it's a rational case.
It's for rational theta.
So, in this famous exchange of letters with you, you wrote a formula for general beta ansatz for general Cartan matrix, but I don't think at the time you knew that you could also put affine Cartan matrix there. And so, yes, because it actually requires an extra parameter. Epsilon 3 is a parameter which only appears once the Dedekind diagram of the corresponding algebra has non-trivial pi1 as a loop. And so it's the additional piece. loop pi1 has a fundamental group. The Dickey diagram is not simply connected. H1. H1, okay. Okay. No, but of course, but it could be, yeah, okay. So it corresponds to H1. It's H1, of course, of course. Maybe Vanya will generalize it to non-abelian parameter. Maybe there is a non-abelian epsilon parameter. So then for for the monster algebras, maybe it will be non-abelian extension. What do you call the algebras which correspond to multiple loops? You know, hyperhyperbolic, ultra hyperbolic. Okay.
Okay.